I want to look at finding the limits of rational functions, a variety of rational functions, and we'll see some of the algebraic techniques behind finding those limits. So we'll do algebraic limits. With respect to rational functions. So let's start with this limit. Determine the limit as x approaches 3 of x minus 2 over x minus 1. Okay, so determine that limit. Well, this is a standard rational function that behaves very well unless you make the denominator 0. And in that case, x would have to equal 1. So if x is anything but 1, the limit is easy to find by direct substitution. Because as x gets close to 3, this x gets close to 3, that x gets close to 3, which means that the numerator is approaching 3 minus 2, and the denominator is approaching 3 minus 1, and that's literally 1 over 2. So this limit is 1/2. Not terribly interesting to evaluate that limit. But most of the time when you're finding a limit, it is pretty straightforward. Okay, so let's look at a more interesting example with respect to this function x minus 2 over x minus 1. You can probably guess we're just going to change this to 1. Because now we can't do direct substitution. We'd be dividing by 0. So this function is defined everywhere except for x equals 1. In fact, it's defined infinitely close to 1. And that's what we're looking at here. What is the value of this function if we get infinitely close to 1 from the left and from the right? So let's take a look here at the left-sided limit. The limit as x approaches 1 from the left of the ratio x minus 2 over x minus 1. And so what happens here is whenever x approaches 1, well, the top approaches 1 minus 2, right? 1 minus 2, which is negative 1. The problem is that the bottom approaches 0, okay? And so we can't leave it like this. This is not going to help us at all. But we're not actually plugging in 1. We're plugging in, we're looking at the behavior whenever x is slightly less than 1. So you can imagine like anything slightly less than 1, 0.9 for example. 0.9 minus 1 is negative 0.1. 0.99 minus 1 is negative 0.01. And you can imagine that the closer this gets to 1, the closer this is going to get to 0. But the key is, if you plug in numbers less than 1, then when you subtract, you're going to get a negative number that's close to 0. A negative tiny number. So you might indicate that with a superscript of a negative. So you get a number close to 0 that's negative. And on the top, you just get a number close to negative 1. Okay? It doesn't matter if it's slightly less than or slightly more than negative 1. We'll see why in a minute. Because what we have here is we have a negative non-zero constant. Of course, if it's negative, it's not 0. We have a negative constant, but on the bottom we have a negative, extremely tiny, infinitesimally small number, okay? So what does this do whenever that happens? Well, the idea is if we have a negative divided by a negative, then we certainly get a positive, okay? And if we take a fixed number, such as 1, and we divide by something extremely tiny, that's like saying, how many grains of sand can you fit in 1? How many fractions of grains of sand can you fit in 1? If you take 1 divided by an extremely small number, a constant divided by an extremely small number, you get an extremely large number, okay? So the left-sided limit as x approaches 1 is positive infinity. It grows to infinity because it's a negative divided by a negative, but you're dividing by a tiny number, which makes the ratio grow, okay? Check it out for yourself. Divide by really tiny numbers in your calculator. Divide by negative 0.000001 and see what happens. You'll get a really massive number, okay? So the left-sided limit is positive infinity. Let's look at the right-sided limit. Just to explore this concept one more time, as we approach 1, the top still goes to -1, and the bottom still goes to 0. But now we're looking at numbers a little bigger than 1, like 1.01. And you can imagine if you plug those numbers in for x, you're going to get a positive number that's close to 0. And similarly, we have a negative divided by a positive. We have a negative divided by a positive, which results in a negative number. And we have a constant divided by a really tiny number, which is massive. So we get negative infinity, okay? So what we can see here is that as we approach 1 from the left, we get positive infinity, and as we approach 1 from the right, we get negative infinity. In fact, if you were to look at a graph of this, right, if you were to look at a graph of this function near the x value of 1, as you approach 1 from the left, your graph's going to go up to positive infinity, and as you approach it from the right, it's going to go down to negative infinity, and that indicates a vertical asymptote, okay? So that's when you can have that sort of behavior. All right, so we've looked at the left-sided limit, the right-sided limit, understanding what happens when you divide by small numbers. Now we have to answer the question, what is the two-sided limit? Well, the two-sided limit does not exist because these are not the same, okay? So the two-sided limit does not exist. And that's a very basic rational function as we apply limits. So let's look at some other interesting examples where the algebra is more useful to us. Okay, let's say we want to determine the limit as x approaches 1 again of x squared minus 4x plus 3 over x squared, how about minus 5x plus 4, okay? Now, you should immediately think, okay, well, let's try direct substitution, right? So it's going to work as long as the only problem we can have with this standard rational function is we don't want the denominator to be 0. So if we plug 1 in on the denominator, we get 1 minus 5, which is -4, plus 4 is 0. So that's not going to help us. So now what we need to do, and we're not even going to look at left and right-sided limits, we're going to look at algebraic manipulation of this. Let's factor the numerator and denominator. The top is x minus 1 times x minus 3, while the bottom is x minus 1 times x minus 4. Okay? And we're taking the limit as x approaches 1. Now, what happens here is we're actually looking at numbers close to 1 from both sides. So for example, if I plug in 1.1, 1.1 minus 1 is 0.1. 1.1 minus 1 is 0.1. Those two numbers are always going to be the same. So they're always going to cancel as long as x doesn't equal 1. If x equals 1, we'd be dividing by 0, which we're not allowed to do. Okay? But we're not looking at 1, we're looking near 1. So whenever x is near 1, these two guys are always the same value, thus they will cancel since we have multiplication and division, which undo each other. And so now, through this algebraic manipulation, I know that as long as x doesn't equal 1, I can cancel those. So this is the same thing as the limit as x approaches 1 of x minus 3 over x minus 4. And so now we reevaluate and we say, okay, now can I plug in? Can I use direct substitution to plug 1 in for my x's? And the answer is yes, because the denominator is not 0 anymore. So now we just get 1 minus 3, which is negative 2, over 1 minus 4, which is negative 3, which simplifies to positive 2/3. Okay, so as x approaches 1 from both sides, this particular function, this rational function, goes to 2/3. And if you were to look at a graph of this function near x equals 1, right, we know it's not defined at 1. We already said we can't plug 1 in. We'd get 0 on the bottom. So I know there's no output there, okay? But whenever I approach 1 from both sides, my y value is approaching 2/3. So what that tells me is I have a hole in my graph, and I know I've got points on either side that are coming in close to that point from both sides, okay? So not an asymptote in this case because we didn't have infinity for the answer, but we got a constant from both sides, meaning that they actually meet up, but it's a hole because the function's not defined at x equals 1. Okay, let's do one more example of a rational function. So now let's determine the limit as x approaches 0 of x plus 2 to the third minus 8 all over x. Okay? It's a bit different looking. Different approach completely. The first example we did, we had to do one-sided limits. The second example, we had to do algebraic manipulation. And here's yet another example of a rational function. And so we always start by saying, well, can I just plug 0 in for x? And of course we can't, because that would make the denominator 0. So what we want to try to do first is let's clean up the mess on the top and see how everything plays out. Okay? So let's try that first. Now, I'm going to give you a tip because I know you find it redundant to keep writing the limit on every step. It's a necessary evil. You need to write that limit on every step. But I think it's commonly acceptable in work to leave off what x is approaching here and just write limit and then reintroduce it later when it's valuable to us. So that's the approach I'm going to take. So what we're going to do on top is we're actually going to take x plus 2 times x plus 2 times x plus 2. We're going to multiply that out and then subtract 8 and see what happens, okay? And I can already tell when you multiply these out, the 2 times the 2 times the 2 is going to be 8, and minus 8, those are going to cancel. That may be really helpful to us, okay? So, but let's not jump too far ahead. Let's start by multiplying x plus 2 times x plus 2, which gives us x squared plus 4x plus 4. So we're just doing this part for now. We still have to multiply that by the remaining x plus 2, and we still have to subtract 8, okay? Now I'm going to multiply the trinomial x squared plus 4x plus 4 by the binomial x plus 2, but I'm going to do it strategically. And what I mean by that is, let me rewrite my limit. What I mean by that is I'm going to take and I'm going to collect all of my terms in order. So if I multiply this by this, the highest power that I'll see is x cubed. And the only way I can get x cubed is x squared times x. So that's my x cubed term. Then I go down to the next lowest degree, which is x squared. I'm going to collect all my x squareds. Well, I can get x squared by multiplying x squared and 2. That gives me 2x squared. But I can also get x squared by multiplying 4x and x. So I've got 2x squared plus 4x squared, that's 6x squared. Those are all of my x squareds. Now the next lower degree is x. I can get x terms by multiplying 4x and 2, that's 8x. And there's 4x, so that's 12x. And last, I can take my constant term, which we already said earlier is going to be 4 times 2, which is just 8, okay? So you can be very strategic about how you multiply that. Just make sure you don't miss anything. Then I still need to subtract my 8. And as we said, what happens is now positive 8 minus 8 is 0. Those go away. And we get, let me see, I'm going to erase up here and come back to it. Okay. I don't know how much room I have on the screen. I hate to go off the screen. So I'll just put dot, dot, dot. We're resuming our work here. So this will be the limit. And now, a couple different approaches. We're dividing by x, and all 3 of these are divisible by x. So I'll just divide them all by x. And so I'll get x squared plus 6x plus 12 when I divide by the x. The other approach is to take the x that's common to all 3 of the terms on top, factor it out, and then cancel the x with this x. Either way, we get this. Make sure you have parentheses here now. Otherwise, without the parentheses, it looks like you're just taking the limit of x squared. Okay? So put parentheses around this. And now I'm going to go ahead and resort back to writing my x approaches 0, because now this is the step where I can take my limit. Remember, I couldn't do it here yet because I was still dividing by x. And x is approaching 0, so I can't plug that in to divide. But once that x on the denominator is gone, now I can do direct substitution to see that I get 0 squared, which is 0, plus 6 times 0, which is 0, plus 12. So the limit is 12. Okay? So there's another example of algebraic manipulation. Didn't involve any factoring. Instead, it involves simplifying the fraction just by distributing and canceling so that the denominator went away and allowed you to directly substitute the value.